Hello and welcome to today's explainer. If you've ever stared at a glass of salt water and wondered what is literally happening down there at a molecular level, well, you are in the perfect place. Today, we're taking a step-by-step journey to completely demystify the fundamental chemistry of solutions. We are going to master how things mix, why some substances seem to just vanish into thin air, and the real science behind the liquids we interact with every single day. Let's dive in.
Here is our agenda for today. We're going to kick things off with the salty sea myth, then look at the anatomy of a solution, and put these mixtures to the filtration test. After that, we'll explore saturation levels, calculate solution concentration, and finally wrap up with our key takeaways.
Section 1. The Salty Sea Myth.
Okay, so to really grasp the science of solutions, it actually helps to start with a bit of folklore. In Philippine mythology, there's this legendary giant named Angelo. And according to the tale, a goddess of the dark asked him to build her this grand, sweeping mansion made out of pure white bricks. To pull this off, he traveled to the kingdom of salt and gathered up millions of pure white salt bricks. He built hundreds of bamboo bridges across the ocean just to transport them. But as millions of men carried these insanely heavy bricks day and night, the bridges finally gave out. The men and all those millions of salt bricks plunged directly into the ocean.
It's an amazing story, right? But looking at the actual science of it, it leaves us with a massive question. What exactly happens to all that salt once it hits the water? Because the bricks don't just sit there on the ocean floor like some sunken building. They disappear. The fresh water of the ocean became salty. This ancient folklore is actually a perfect bridge between storytelling and the real-world observable chemistry of mixtures.
Section 2. Anatomy of a Solution.
So in any solution, you basically have two main players, the solvent and the solute. I absolutely love using this simple analogy for this. Just imagine a solution is like a party. The solvent, that's the host of the party. The host's job is to welcome and accommodate the guest. The solute, on the other hand, is the guest arriving at the party, the substance that is actively being dissolved and taken in by the host. So thinking back to our ocean myth, the massive ocean water is our welcoming host, the solvent, and the salt bricks, those are the guests, the solutes, being dissolved.
Now, if you're ever staring at a chemistry problem and you get a little tangled up about which is which, here is the absolute easiest way to tell them apart. Just look at the amounts. Seriously, it's that simple. The solute is pretty much always the smaller amount in the mixture. It's the stuff being dissolved. The solvent, our host, is the greater amount in the mixture. It's the material doing the dissolving. Like if you mix a single spoonful of sugar into a giant pitcher of water, the water is clearly the greater amount, so it's the solvent.
Section 3. Passing the filtration test.
To put these mixtures to the test, scientists use a standard filtration setup. We basically take a mixture and pour it through an everyday funnel lined with filter paper, or honestly, even a simple cheesecloth works. Now, if you were to mix, say, mango seeds and water and pour it through, the seeds would get totally trapped in the paper, right? But if you mix salt and water until it perfectly dissolves and then pour that through, it passes completely through the filter. The solute and solvent literally cannot be separated by physical filtration.
And passing this filtration test is exactly what confirms a mixture is a true solution. A true solution has a totally uniform appearance. It looks exactly the same from top to bottom, only a single phase is visible. That just means you don't see floating chunks of solid. It just looks like one unified liquid. And because it's so perfectly mixed at a molecular level, the solute cannot be separated out by a filter. In chemistry, we call this a completely homogeneous mixture.
Section 4. The 3 saturation levels. Okay, I want you to visualize something with me. Imagine adding spoonful after spoonful of sugar into a glass of water, continuously, over 10 minutes. At minute 1, you add a spoon, stir it up, and boom, it vanishes instantly. This state is what we call unsaturated. The host water can still comfortably dissolve way more solute. But by minute 5, you've added so much sugar that when you stir it, it just swirls around and settles stubbornly at the bottom. The water simply cannot take any more. We call this saturated. The maximum solute limit has been officially reached. Now imagine by minute 10, we actually heat the water up to literally force it to accept even more sugar, and then we carefully let it cool. This creates a highly unstable state called supersaturated. There is way too much solute in there, and if you drop even a single extra grain of sugar into it, the whole thing instantly thickens and crystallizes right before your eyes.
Section 5. Calculating solution concentration.
So, whenever you're asked to calculate the actual concentration of a solution, whether that's percent by mass or percent by volume, you can always rely on this simple, foolproof 4-step method. Step 1, always identify your given data first. What's the mass or volume of your solute and your solvent? Step 2, identify what is asked. What is the specific question trying to find? Step 3, write down the correct formula. And step 4, substitute the data into your formula and just do the math. Sticking to this process keeps your work neat, logical, and accurate every single time.
Let's actually apply that right now. Say we have a sample problem where we dilute 7.5 milliliters of hydrochloric acid into a total 100 milliliter solution, and we need to find the percent volume. Step 1. Our given data is 7.5 milliliters of solute and 100 milliliters of solution. Step 2. We're asked for the percent volume. Step 3. Our formula is the volume of the solute divided by the volume of the solution multiplied by 100. Step 4. We substitute. 7.5 divided by 100, which is 0.075. Multiply that by 100, and we get our final answer, 7.5%. See how simple that is when you just break it down into steps?
Section 6, Recap and Final Takeaways. All right, let's take a second to visually map out everything we've absorbed today. At its core, a true solution has a uniform appearance and a single phase. Remember, that's what makes it a homogeneous mixture. Second, a true solution cannot be separated by physical filtration. Those solute guests pass right through the filter paper with the solvent host. And third, solutions have very real saturation limits. They can be unsaturated, saturated, or supersaturated, all depending entirely on the ratio of the guest solute to the host solvent.
And that brings us to the end of today's explainer. But before you go, I want to leave you with this one thought. We started out with the myth of an ocean turning salty from millions of dropped bricks. Science tells us that the ocean is really just one giant, massive solution holding billions of tons of dissolved salt in a single uniform phase. So if water is such an incredibly powerful host solvent, what invisible solutes do you think might be hiding in the water you drink every single day? Keep questioning, keep learning, and I'll catch you on the next explainer.